Yeah. Yeah, so yeah, David is in Bayer is going to give very precious history of in his career path. So along with some brief introduction of his side. So yeah, this will be helpful for so your determination, your career path, as well as some information of maybe some internship or job information from this company. Okay, yes, maybe.
I'm going to share screen here.
Yeah.
So maybe I'm going to try to share a screen. Let me try that again. Share. Okay, I didn't. Must have hit the button before. So you guys can see my screen. So I'm with Bayer Crop Science Division in Kansas City. This is on the east side of the Kansas City near 435 and Front Street. And I've been in and out of that site for many years now, as I'm suddenly an older guy. So I'm first going to talk a little bit about career-wise. So, if you talk to, other folks I graduated with, or I'm on the advisory board for the chemical engineering department, and you start talking with people and their careers, one thing that's really kind of remarkable is the number of different paths that a chemical engineering degree can take you. So people like myself, doing, I'll say, hardcore industrial organic chemistry. There's folks who went like more in petroleum. There are people who go and do things around medical devices, building airplanes, all sorts of different crazy paths. So I can talk about one possible career path, the career that I had taken. And I spent, I've been with Bayer now for, 30 some years. And I've done quite a bit of taking lab chemistry and making that on an industrial scale. So doing a whole lot of what we in the chemical industry, you call it fine chemicals, and you're taking relatively large organic molecules of your product. So I'll kind of talk about that as I go on. So I graduated in '85, and by the end of my junior year, I actually got a summer internship with Bayer, and I can't stress how important it is if you have the opportunity to make the opportunity. And not everyone, just a little bit of dumb luck is involved. But if you can do an internship, or even better, a co-op where you're doing 6 months at a time, it's longer period of time, and it's more than twice as valuable to do the co-op versus the intern for both you and the company. And I had the opportunity to join for a summer. They liked me enough to have me back for another summer. And then I had plans to go on to graduate school, but they said, hey, why don't you just work here for a while before you go to grad school? So I stayed for, I don't know, about 15, 16 months. And then this time I'm working where Nathan was working, down in environmental operations. So this is wastewater treatment, incineration. At that time, we had a carbon unit with a carbon furnace, which is a lot of interesting things that were new and different to me. And that was great experience. And so I was talking at another meeting earlier today. The interim dean invited some of us to talk. And it's interesting, you come out with a 4-year degree, and part of me, because I'm naturally wired to be somewhat overconfident, you come out with an undergraduate degree and think, okay, I'm a chemical engineer. And what I found over and over again is, no, you're not really a chemical engineer yet. You don't know anything. You haven't really worked that much. And so I worked for, while I'm working for a couple of years in a 4-year degree, and I go back to graduate school, and wow, that's really challenging. And there's a lot of stuff that I don't know, and I'm surprised at how much I don't know. And then, I come out with the graduate degree and have a couple of years of experience. So, okay, now I really know some stuff. And I went to Charleston, South Carolina at a Bayer was a Bayer facility making organic dyes and pigments, a lot of really, again, so I'll call it hardcore organic chemistry, multiple steps, different, organic chemical reactions. And I'm a plant engineer in Charleston. I started as an environmental engineer. I didn't last a year at that. I didn't realize what an environmental engineer does. And it was a whole lot of reporting and a whole lot of reading regulations. And I like hardcore chemical engineering. I mean, to me, some of the stuff that you're doing in school is like crossword puzzles. Some of it I'd do it for free, just for the fun of it, because I'm just that nerdy. But I tried environmental engineering. I thought this would be great. I can make money and do good things for the environment. And I hated it. I absolutely hated it. So the moral of the story, I guess, is you can take a branch and a career path, and sometimes people can tend to lock in on it, kind of whether they like it or not. And I did not like it, and I was clear that I did not like it. So I started politicking really hard and really quickly to become a plant engineer. And not that long afterwards, I was a plant engineer. And in those days, a plant engineer you were kind of a generalist. So there were no process engineers at this plant. So I did process improvement stuff. I did maintenance. I did small projects. I was kind of the engineer. It was a great learning experience because you did kind of everything. And I learned a lot through that. But if you get in that spot where you get a job, right now you're thinking, I'll take any job. I mean, literally any job that needs a chemical engineer. And yeah, do. But once you've got that job, don't particularly stop looking unless you just really love it. You should think about it. And I've moved around a lot during my career. And if you're more in a job, particularly early on, 2 to 3, 4 years should be your target, unless you really love that specialty and that's your thing. But even if it is, try something else, you might like it better. And if you're unhappy, certainly don't put up with that. So I was in Charleston for about 7 years, doing different things. Built a wastewater treatment plant. I didn't build. I was on the project team. Did a lot of interesting thing with mostly batch organic chemical reactions. It's just, and in that world is just, if you take an organic chemistry lab, I did a lot of, particularly coming to the next one, I started working at a pilot plant. I did a lot of, here's a lab procedure. Literally, I would get a lab procedure. And the question was, hey, you have some idle equipment, you have some 3 reactors and distillation column and a centrifuge. Is it possible for you guys to make 500 tons of this stuff in a year? And if so, how much would that cost? And do you have any, how much of the project cost? How much will the product cost? How quickly can you get it done? Can you deal with the safety concerns? A lot of safety concerns around some of that. So I did a little bit of that as a plant engineer. When I came back to Kansas City in '95, I was invited back. And I went into the process pilot plant, which is now sadly for me, a gravel flat spot where the building used to be. But in the pilot plant, you did exactly that. So I worked in tandem with a laboratory with this PhD chemist with a lab tech. And I had the pilot plant equipment and operators. And there again, one of the things that was great about that, I was the engineer. So you designed you did the PFD and the PNID for the unit. You wrote the procedure. You did the chemical engineering, what chemical engineering there might be, heat transfer stuff, distillation things. I really learned distillation in the pilot plant, where you had a lot of glass equipment, so you could see what was going on the inside. So in unit ops class, you'll hear about flooding, but there's nothing like seeing it in a glass column where suddenly the liquid won't go down anymore because the vapor is going up too fast and what that looks like. So that was super interesting. So I did a number of probably 12 different chemical reactions, 3 different products, each like 4 multi-step products. And literally I'm getting a lab procedure and I'm transforming that into a plant procedure with the plant layout, doing safety reviews, making the stuff, writing reports, doing a lot of fundamental chemical engineering as part of that. Because what you'll find is a lot of jobs, like when I'm a plant engineer, a lot of that job was simply maintaining an operating plant. And there's not quite as much chemical engineering as you would get when you're doing like a pilot plant or project design, where you're doing a lot more I call hardcore chemical engineering. So I did a product scale up. So we went from the lab to the pilot plant to the full scale industrial scale, and that was really fun and interesting. And I learned a lot. Did some pilot plant work for high active herbicide, and then I went from doing the scale up to a pilot plant scale, and then I got put on the project as basically doing the process design, and that was super interesting until we had been all the way through HazOps. We're getting equipment quotes back. We're getting really ready to start engaging construction, and they pulled the plug on the project, which was very disheartening. But that happens too. So in 2000, I then became a plant manager, assistant plant manager, and then I'm more running the full industrial scale stuff. So I'm in a plant. I'll show you a picture here in a little bit, and Nathan's seen the Sencore plant. So I was a manager for the Sencore plant, running unit operations. So I think at the time I had about half the plant that I was actively managing, and you've got process engineers and operators and supervisors and all sorts of other people in support of that. And that was interesting as I started in that job, get a little bit more into the leadership thing, where prior to that I was largely, almost exclusively technical, and then as assistant plant manager, I didn't have people reporting to me. But I had people looking at me and calling me boss. So really looking for direction and all lots of leadershipy things. So I guess another thing that you talk to people like myself who've been out for a while is you never stop learning. And then, by the time I had worked in the pilot plant, done some scale ups, I mean, I really felt like I was at that point, I was a chemical engineer. Like I knew some stuff. I could do some, I could on my own do a whole lot of stuff. And then you go into management, and I'm still highly technical in that assistant plant manager role, but start to see some leadership. And then you go, oh, I have a whole nother thing here to learn that I didn't even consider, which is leadership, which is really different. So running plant, you'll learn a lot of other different things, and you start to get experience. One thing I'll say too is the difference around safety in a plant, and I'll talk about safety a little bit, but the difference between 1984, when I started as an intern, and 2014, there's a lot of difference in terms of safety working in a production environment. It's night and day, really. And a lot of the things I can tell stories on myself from 84 and 85, when I get to 2014 and tell us, or 2021, tell those stories, people look at you like they can't be possible. There's no way. I don't believe you even. Well, things are definitely a lot better. So I was assistant plant manager for a few years, and then I had an opportunity to go to Germany as an expatriate. And that was an interesting experience. And off to the right here is a plant called Zato, and that's German for Central Organic Pilot Plant. And it was a very, very large pilot plant. So Nathan is like the pilot plant the size of the Sencore plant. And in that plant, they did 150 different chemical reactions a year. Again, it's all organic chemistry. And every year on year, about half of them had never been done before. So sometimes you'd have reoccurring production, but most of the time you're doing something that's often we're developing in the lab and then doing it in the plant as part of the overall process development. And that was a super interesting job where I never spoke a word of English to anyone. So I got really fluent in German by force, but I wanted to do that. That was fun. But then you're learning a foreign language and furthering leadership skills. While from a technical standpoint, those 3 years I learned more than anywhere else because you're doing so many different things all at once. And then in 2007, expat job was over. I come back as the lead plant manager for the Sencore plant in Kansas City. And then suddenly I have 100 direct people who are reporting to me. And that was a little bit of a shock, going from a couple of people in Zato and no people before that to suddenly 100. So you're learning a lot. And we had a lot of challenges of different kinds. So 7 years as a plant manager, again, learned a ton. And I had to say had an impact on particularly around the operating safety of the plant. And then in 2014, 7 years of that was a lot. That was a really hard, stressful job. And then since 2014, I've been the head of quality, safety, health, and environmental, which has been completely different. I've never had you can say I've never had a staff job where I wasn't in a plant. I've been a plant of some sort or another since an internship. So that was a real change for me. But it's also been interesting in a different way. I didn't know that I would like it because I went back to my environmental engineering job. But what I find is it's interesting to have a different perspective. I'm not in a unit. I'm looking at the entire site and sometimes looking outside of our own operating site. So it's been interesting in a different way. So I just talked a whole lot. Do you guys have any questions or thoughts on that part?
Just just a little comment. Yeah, so it's it's amazing career you have. So it's okay. So as a chemical engineer, because you start from fine chemical to the large plant, and also starting from the small operation to the manager and leadership manager, and also working in in outside of your country. So is it still the same company and that you just okay.
Yeah, no, actually, and that's highly unusual for someone to work for a single company that entire time. But yeah, I worked the entire time with Bayer, and it's been a good company. Also, I grew up in Kansas City, so I left. I never expected to come back to Kansas City, but it's nice because I have family and friends here, and there's not much for a chemical engineer to do in Kansas City. A couple of big consulting companies. But no, it's been actually a really good company to work for. So no complaints.
Yeah, it's a very great career to share with students. Okay, any questions, Nathan, Josh? Yeah. Okay, yeah, you may go ahead.
All right.
Yeah.
So a little bit to the Kansas City site. I talked earlier about safety. Well, this is pretty normal. If you look at any data for like the American Chemical Council puts out data like this for different, for industry, and they all look about like this. So, imagine you go back, this is starting in 1994, 10 years earlier. Well, guess what? It was higher yet in terms of injuries per year. So we've gotten to the point now where we're down to, 4 plus or minus a couple injuries. I think we had 3 last year. We haven't had any yet this year, but in our injuries, are really mostly minor cuts, falls, back strains. And once in a while, I get more concerned now when we have an almost something that happened. It's the difference between a recordable injury and a lost workday injury and a fatality and nothing at all. Sometimes it's just a few seconds or a few inches can make a huge difference. So if you have some of the near hits, we're getting more interested in things that almost happened that could have been severe than we are about a recordable finger cut that was never going to get more than that. But interestingly, you know, when I remember as a junior, I looked at doing a design class, and I saw an ammonia storage tank like an article on an ammonia storage tank that came apart and released a huge amount of liquid ammonia, which vaporized and killed a bunch of people. And I was like, holy crap, this chemical industry. I never really thought, you know, as a chemical engineer, I'm going to be working in a chemical plant that could be maybe not real super safe. And you know, back then it was definitely a lot less safe, just in terms of practices and what we do. Now in industry and bears, we're not really exceptionally great. We're good. I think we're really good, but we're not really different than the rest of the industry in that, you know, we've gotten to the point now where the most dangerous thing that we have in our chemical plant, the most dangerous thing really by far is gravity. Someone falling or something falling on someone. And if I think back about the last 3 or 4 injuries, three of the 4 where something fell on someone or someone fell. So that's kind of where you're at. It's a chemical plant. It's really dangerous. Yeah, there are a lot of hazards. The most dangerous chemical in terms of chemical burns by far, I think, is hot water and condensate. Is if 60 degrees Celsius water hits you, or 90 degree or 100 degrees Celsius water hits you, unlike if sodium hydroxide, 50% sodium hydroxide, I've seen all of this, lands on you and you wash it off relatively quickly, your skin might be red, but it's not gonna be as catastrophic as we think. Hot water, instantaneous. There's no washing it off. It just happens right now. So if people underestimate that. So we have things like trifluoroacetic acid, which is terrible stuff, terribly corrosive, poisonous. No one ever gets hurt with that material because everyone says, oh, it's trifluoroacetic acid. Let's be super careful. It's all sorts of preparation stuff. But hot water and condensate, we kind of get, well, it's just water, and we get real casual with it. So, and then, so from that standpoint, our people are literally safer. We have had more people hurt badly at home than at work. So that's just that, you know, because we do all sorts of crazy things. You know, we don't tie off ladders and wear safety glasses at home like we should. So we spend a lot of time also around process safety. We engineer a lot of safety in that we used to rely on people. So more and more we're relying on computers rather than people. So if you're in an interview and they're saying, you know, what's important to you? If you say safety, like process safety and occupation, it is really super important to me. And you can also then follow with why. You'll get extra brownie points with any company you interview with. I virtually guarantee it. And if you don't get brownie points with that company, probably not someone you want to work for. Just saying. So enough there on safety stuff. So this is a Kansas City site. Looking to the north, there's a little Blue River along the south, and along the east side is a Missouri. Up here, you can see this is a coal-fired power plant that probably won't be our neighbor for much longer. I don't know, maybe 10 years I give them, but somewhere in there the coal plants will go away. And then here's the boundaries of our site. So I'm going to flip views here a little bit and go. This is looking from west to east. I think I've got, if I do one more, yeah. So this site was built back in 1956 in this area, and then slowly expanded. We have something like 550 people, depending on how you count them. We have some contract people, but generally speaking, it's been about 500. We work, let me go backwards one, or for crying out loud. So we'll have a lot of people working shifts. So like most manufacturing sites, we're working 24/7 every single day of the year. Christmas is just another day. And that's also quite normal. Now, if you're a chemical engineer, a process engineer, or manager, then you're working days. Increasingly, you're working from home. And we'll see how that looks a year from now. I'm curious. And Christmas is a thing. So yeah, life's not always fair. So our site is made up of 2 active ingredient plants. So this is site 1. In this area, we're making high active herbicides. So there's 2 different herbicides that are similar chemistry. There's 4 reaction steps, and then we do a couple smaller products as well. What's nice about a high active herbicide is just like 5 grams an acre, if you can imagine. Like a teaspoon of stuff kills weeds in like an acre area. So not much chemical goes on the ground, which from an environmental fate of the chemicals that you put on the ground, what happens to them? If you're not putting much chemical on the ground, that's generally seen as a good thing in lots of different ways. So here we're making high active herbicides. Dollar value per kilo is extraordinarily high, and you're not making a lot of stuff. So this is almost to the point where it's kind of somewhere between normal agricultural chemicals and pharmaceuticals in terms of dollars per kilo. It's getting really expensive. The other active ingredient area is a Sencore plant. It's called that because that was the first product that was made in it. This place is built as a single plant, a single product plant, and over the course of time has morphed into to 1 product to 2 products that are switching back and forth. A 3rd product gets put in both ends. There were some openings for future expansion, and then we put another product in, and we're switching things back and forth between 2 different products. And then more capital expansion. I guess the where I'm going is in our business, product life cycle is a thing. And if you're an old guy like me, you've seen products that were like new and coming out of process development, literally. Like one of the products I did the piloting on is still made in the high active herbicide plant, but we're talking about phasing it out. So there's always products coming. They're new. You make a lot of money. They go off patent. They become generic. Some other new products come and take the market, and then you're not making a lot of that, but then you have another new molecule to make, which that kind of change makes it interesting if you're a chemical engineer. So this plant, this is the other active ingredient plant. So in this plant, in both these, we've got, and I'll show you some pictures. We're doing batch reactors and continuous reactions, distillations. We're isolating most of the product. These organic molecules look like sugar or, I don't know, cocaine. They're all like white powders, these big organic molecules. We're generally isolating them on a filter, mostly in this plant it's centrifuges. Mostly in this area it's like a Nooch filter, which is a different kind of filter dryer. The only operations that we don't do in the active ingredient area that I think of, we don't do reverse osmosis of any kind. Otherwise, just about every unit operation you can come up with, we're doing liquid extraction, on and on. So it's, again, from a chemical engineering standpoint, it's super interesting. We're also doing in formulations. Then we're taking that white powder, inevitably our products are white powder, grinding it up into very fine, really fine particles that don't sink very fast, adding a bunch of things that make it thick and suspend. And then we're making mostly suspended concentrates. We're making a 50% active ingredient. So at 50% organic chemicals, about 20% water, about 30% other stuff that sits there, it flows. It's really a solid in suspension, but it flows and looks like a liquid. It could stay there for 2 years. It'll still look like a liquid. You don't have to shake it up. So it's some interesting physical property stuff that's done over there. And then that product gets shipped out to the farmers. And then here on site, also, Nathan's a little bit more familiar with this. This is where we have wastewater treatment plant. So we settle out solids, go through biology back here in the back. We have an interesting pure oxygen system for biology. We go then through carbon filtration before we go our effluent goes out to the Missouri River. And interestingly, then we run things like wet tests where we take our wastewater and dilute it down to like what would be in the river and see, do these really sensitive organic, really sensitive microorganisms, can they live and reproduce in that water? So test kind of toxicity and lots of reporting for our environmental engineers. Then we have a thermal oxidizer, a liquid down-fired recurrent incinerator, and also a vent gas incinerator. So, some of the chemistry we're handling, we generally speaking, we're always venting to an incinerator with the active ingredient areas. We never just vent out. We're not just venting out through a scrubber. You just don't get the efficiency. Any questions on that one? I got more. So if you have a question, just interrupt me or raise your hand or whatever. So here's wastewater treatment plant, just to give you a little feel for it. Down-fired incinerator. And this is interesting in that normally you won't see an incinerator like this on a production site. Most of these you'll find at commercial incineration. That's what they do. They'll have maybe 2 or 3 of these kind of incinerators, and people send hazardous waste to them. But we generate enough because we're doing a lot of steps of chemistry, and each one, if you remember back to reaction kinetics or whatnot, you've got reactant A plus reactant B goes to C. Well, some of it goes to D, and then B reacts with the product to make E. And so some of those, if you get 90%, 95% yield, that might be pretty good. The other 5% makes waste that you have to then deal with. So that's why we have an on-site incinerator, just mostly because of the chemistry is not very clean. So we do a lot of different steps. So we have 9 different active ingredients that we produce. We do chlorinations, methylations. We're adding a methyl group of things. Grignard reaction, which is an organometallic, use magnesium as a reactant or a carrier. I don't know what you call it exactly. Things like hydrogen peroxide and coupling reactions, and the list goes on. And then we have also then a number of hazardous raw materials, chlorine, anhydrous HCl. You can read the list here. And again, what I always find astounding is when people are starting to work around these chemicals, then everyone stops, and we think and we talk a lot about it, and we write procedures, and people put on all sorts of extensive PPE, and then we start thinking about going after it. Where again, kind of some of the more chemicals we get used to, we can be a little bit more casual with. So here's this is a model that actually the Sencore Plant we saw a picture of. So this is what, on the inside, this is what the plant looks like. And increasingly, we used to, when I was a young guy, we're going to build a plant like this. We build a plastic model. Literally, we build a plastic model of the plant, which sounds crazy, but that's just the way it was done. Now, these days, it's all virtual. So this is a 3D model of the plant. And when we're doing, this was actually made, we installed yet another new product in the Sencore plant here a couple of years ago. And what's fun with this is when you model a plant, you can actually, when you're doing the drawing reviews, people you literally, you don't really put on goggles, but you probably be better if we did. But we're actually taking screens, and you can actually kind of virtually walk through the plant before it's built and see, hey, does this valve look right? And does it look like we'd have enough room to get that reactor out if we had to replace it? So kind of do a lot of interesting things with technology now. And then just as the final slide, we make a whole lot of different stuff. So we make 120 different products. The active ingredients that we make are often shipped worldwide. And then we have other plants in the Bayer network that are sending us active ingredients that we formulate into products. And normally this is why I'd say, okay, let's go walk around and we do a plant tour, but that's not really possible right now. So you guys have questions? Sorry, I went over a little time, but.
Okay, yeah, you're great. Yes, it's very great. So then, okay, you currently have about 120 products right now in your site, from 120 products?
Yeah, well, there's 9 active ingredients. And each of those, we do 30 steps of chemistry total, those 9 active ingredients. So, you may have a couple steps. For one, we have 7 chemical reactions in series. So you did this reaction. Some of them are continuous reactors. Some of them are like CSTRs. Some of them are batch-wise. Some of the reactions are in like tube reactors. All sorts of different times. So 9 different active ingredients, and then formulated products. We're taking some of this active and some of that active. We're milling it down and putting it in a jug. We have 120 of those that are different. So a lot of complexity to manage.
Okay. Okay, then I don't know. Maybe this is just very broad question. What is the typical lifetime of the one product, such as you cannot sell one product for the entire time. Maybe you have to switch to some new product. So what is typical the cycle of?
It could be as short as 20 years. It depends on the product. So the plant that was built to make Sencore is still making Sencore. It was built in 1975, but a fraction of the Sencore that was originally made. So it's kind of, you'd say, probably on its downward cycle in terms of life cycle. But then there's the high active herbicide that I did the piloting on in 2000, and it's getting pretty close to going away. So it's more like 20 some years.
Okay, yeah. And any questions from students? Josh, Nathan?
You have to ask at least one, like, what's your favorite color or something? Come on. I think they've fallen asleep totally.
I just can't think of anything. I think you did a great job presenting it.
So just you're going to see that so in your class. So so pretty much this site has every single some operations you're going to learn in your class. So that's everything is here. So that's why you have to learn so many things in your class. That's what I want to say right now.
Yeah. I have to say, I've used a lot of what I've learned. A lot of it, I've done a lot of calculations. God knows how many. A lot of it also just has to do with coming away with a physical understanding of what you're talking about. I solved a problem when I was back in Bushy Park. It was vapor liquid equilibrium problem. We were having cavitation damage to a glass ion reactor where it's spinning, it's near the boiling point. Behind the baffle, those lower pressures, so the bubbles would form. And then they would collapse and make little mini explosions, and we're tearing up the glass. Well, kind of understanding, hey, well, we're really close to the boiling point. No, so let's just put that reactor under 5 pounds pressure and no more damage. So a lot of it's just understanding, getting a gut feel for what the math is going to tell you is helpful. Some of that you get through experience, but
Okay, thanks so much. Thanks so much for doing this. So
no problem.
I'd like to also share in this video trying to share in this department. So then if students have questions also, so feel free to contact him. Okay.
Yeah, sure.
Okay. Thanks so much for giving this presentation. So have a nice day. So
all right, be good.
Yeah.